All right, so we've been talking about radiation and sources of radiation and nuclear processes that can emit radiation, at least a little bit. Today I want to talk about how radiation interacts with matter. So let's assume we have some radiation, and we know there are different types of radiation. And now the question is, what happens when it encounters material? So, of course, in vacuum, it can just propagate. Now, the vacuum isn't as empty as it sometimes might appear, but certainly less empty than massive objects. And so what happens when radiation encounters material? So what does the radiation see? And that of course depends. So I want to ask you, if you go out somewhere, stand on a field, and in the distance there's a forest, what do you see? Just a little bit of green and brown and different colors. You can't necessarily make out individual trees, right? So then as you go closer, you can see trees. You can't really see the entire forest anymore. You have a couple of trees in your field of view, but you don't really have a good view of the entire large forest anymore. And then if you get even closer, you put your nose up to a leaf, you may see that leaf or that twig or that part of the tree. Really, you can't see the entire tree anymore, and you certainly can't see the entire forest, right? So in this case, in this example, the different length scales you resolve, either a leaf or a tree or the entire forest, is due to your proximity to the forest or to the tree, right? But it could also be due to just the wavelengths of light or the wavelengths of radiation you use to look at the structure. So we've discussed that photons come with different wavelengths, and the different wavelengths correspond to different energies. And so Hc is this 1240 electron volt nanometers, right? A useful constant to convert back and forth. We also can assign a wavelength to massive particles. That's the, to electrons, to protons, to anything else. That's the de Broglie wavelengths, right? And so we can convert energy into a length scale that resolves different structures, right? And so if I have very low energy particles, be it thermal neutrons or be it photons of some average low energy, what are they going to see? Well, they aren't going to be energetic enough to penetrate into the atom to see the nucleus, right? They are just going to see the entire atom, right? Well, neutrons, maybe not so much, but with photons, at the lowest energies, I'm going to just interact with the entire atom, right? Then if I get to higher energies, I may interact with the nucleus, right? But with the entire nucleus, not individual nucleons, right? Or smaller structures. But then if I get to even higher energies, I may interact with, just individual protons and neutrons and so on, and to successively lower length, smaller distance scales and higher energies correspondingly. So let me just share one graphics that kind of makes that point. And it's, okay, it's actually in German, but at the smallest energies, just about 40 keV, 0.04 MeV, we have collective coordinates of an atom. For example, I may excite a rotational state of a uranium atom or something like that. So, so those energies correspond to interacting with, the entire object. Then maybe at something like 1 MeV, a much larger energy, right? A mega electron volt, I may see currents and densities of nucleons inside the nucleus, right? And so that's maybe a vibrational state inside some nucleus or something like that. Then at even higher energies, a couple of MeV, I'm going to see individual protons and neutrons, and I can separate protons or neutrons out of a nucleus, right? So that's the separation energy in lead, right? We looked at the binding energy per nucleon is, can be something like that, right? And then at even higher energies, when I interact, when my particle of radiation comes in with an energy of 135 MeV, now I have enough energy to create the mass of a pion. And so I can interact and my radiation can create new particles in that interaction. And so I interact with baryons and mesons, with the heavy hadrons and light hadrons, right? And then if I get to even higher energies, if my energy is about that of the mass of the proton, I can resolve even smaller structures, and I can start to see that nucleons are made up of constituent quarks. And then at even higher energies, at even smaller length scales, I may actually interact with the quarks and gluons, right? And so, of course, quarks and gluons are inside the uranium nucleus as it's rotating. But what's relevant, what's the right way to describe the system, that depends on the energy of my radiation, right? So, all right, so 135 MeV, that's much larger than any energy of an alpha particle or anything that can come out of a radioactive source, out of a nuclear decay. But we are concerned with the environment in outer space. So what does radiation in outer space look like? How many particles do we have with high energies and low energies and so on? What do you think? Should we be more concerned about particles with very high energies, or should we be more concerned about particles with very low energies?
It depends where you want to break high and low, but I know protons peak at around 1 GeV. And they're like in that region near GeV, there's about 10 to the 4 per square meter of surface area you've got.
So the flux should be per area and per angle, right? Well, however you can integrate over the angle, integrate over a hemisphere and then have your square meter hit from any direction, right? And so you can quote numbers in different ways. Okay, but so it peaks at fairly low energies, right? The GeV, not that much energy. Do we have particles that have higher energies?
We have data out to several thousand GeV, I believe.
Right, and even higher than that. So really there's extremely high energies are possible. They are just very unlikely, right? However, if particles with those high energies strike material, we've seen once we get above GeV or so, we have enough energy to produce new particles, right? And so we can produce hadronic interactions where, say I have a particle of 100 GeV coming in, I may produce loads and loads of pions and kaons and other mesons and baryons, right? And so although the spectrum falls off steeply and the high energy particles are less common, they still have the potential to do a lot of damage because they kind of multiply when they encounter material and start to interact, right? So from one high energy particle, I can get many lower energy particles. All right, but still what we have mostly is low energy particles, right? There's just many more of them. So let's look at how we can describe the interaction of particles in matter, okay? And let's now focus, at least initially, on fairly low energy particles, all right? So what's going to happen? I have, say, an electron, beta decay producing an electron, or also higher energy electrons from other processes. How is the electron going to interact in matter?
It's going to interact almost exclusively with E&M stuff, and so high energy electrons, I know from taking plasma physics last semester, can start to produce cascading showers.
So showers of particles. Okay, so why would an electron produce a shower? What's an electromagnetic shower? So let's so what's matter made of? Of course, the nuclei of atoms and then all the electrons around it, right? So most of the space is filled with electrons. Now let's model our electrons by taking a cardboard box and fill it with loads and loads of ping pong balls, okay? All the ping pong balls are my electrons. And now I toss one electron into that box. What's going to happen? I have my ping pong ball hitting one or two other ping pong balls, and it imparts momentum into those, and they are all going to hit one another. And pretty soon I have half the box of ping pong balls moving, not just one electron moving anymore, but all of them, right? And in the field of these electrons, I have Bremsstrahlung radiation. and I have pair production processes. As long as the electron still has more than the pair production threshold, the mass of an electron is 511 kilo electron volts. So as long as my electron still has more than an MeV of energy, it's going to pair produce, and it's going to produce photons by Bremsstrahlung radiation. And so I have my photon or electron, and it's going to produce electromagnetic showers by producing either an electron-positron pair or by slowing down as a charged particle and emitting a new photon. And each of these can cascade to do that same process. And so it's like tossing a ping pong ball into a box of ping pong balls. It's going to slow down quickly, disperse its energy very efficiently over a relatively short range. And the other end of my box is going to remain pretty much stationary, right? It's not going to move a whole lot far away. So the electromagnetic shower has a fairly short range, characterized by some number that's basically given by the electron density, right, in the material. And so that's how electrons interact. Kind of makes sense. I didn't put a graphic, and I want to just kind of give a rough idea, not go into too much detail, but you can envision how you end up with a cascade of more and more particles until the energy gets dispersed. All right. Let's contrast that with how a proton interacts in this scenario. So now I still have my box of ping pong balls, but I'm tossing a bowling ball into it. What's going to happen with my bowling ball? It's going to catapult electrons out of its way, right? And it's going to barrel down the box in a straight path, right? So the proton is still going to lose energy slowly by imparting energy onto all the electrons, but it's not going to produce a cascade of many, many other particles. It's losing energy, but it's keeping going itself in a straight line, more or less, until the end. So there are different processes. The interaction of my proton or alpha particle or other heavy ion in matter, that's governed by the Bethe-Bloch equation. And so we have initially this very fast particle that's just pushing some electrons around and losing some energy. And so it's not quite as fast anymore, but it's still pushing all the electrons out of the way. And so initially it's going to go so fast past all these electrons, it's not going to spend a lot of time interacting with them because it's moving past so quickly. And so it's actually not very efficient at losing its energy. It's actually what's called a minimum ionizing particle. It's pushing some electrons out of the way, leaving ionization trail behind, but it's not very efficient at dropping its energy. Only when it slows down close to having lost all of its energy, then it's moving slower, and then it's spending more time. And so now it's going to interact with more of the electrons for a longer time. And so at the very end, it's dumping the remaining energy very quickly. It's not anymore minimum ionizing, but it's highly ionizing. And so it's going to cause much of its energy to be deposited close to the end of its path. That's called the Bragg peak. So that was a very quick summary in just a couple of minutes of the process of two of the processes I want to go into more detail, two of the ways, electromagnetic showers and just ionizing the material a particle passes through. But what about higher energy particles? What if what we've described now is so far is processes that happen through electromagnetic interactions, right? And of course, as I'm going through the material, I may encounter an electron closer to my path I'm traveling or further away. It's not totally homogeneous, but there are enough electrons. I can just talk about the electron number density in the material, and that's giving me a good representation. So I can talk about radiation lengths or about an interaction lengths, a mean free pairs in the material, right? Or radiation lengths. But now for higher energy particles, for the high energy proton interacting with the nucleus and producing a bunch of new particles, there is a cross section for that process, right? But for any given proton in the way, my radiation can either pass by or it can interact. And there's a given probability for each of those processes, right? So eventually at the low energies, we understand pretty well what's going on. But at the high energies, I have so many different processes that are available for what can happen. And each has a different probability. And so that's where things become a little bit complicated. And so at those higher energies, I have to really be careful how to model things. And it may be not just one number that characterizes what's going to happen, but it may be a bunch of different cross-sections for different processes that can happen, different nuclear interactions. Those cross-sections may be different for different materials I traverse. So I may have a larger cross-section on one material, and then I change as I'm crossing through the different layers of a spaceship or whatever, or a satellite. I encounter a different material, and now I have a different cross-section. So then we need to model those processes in different ways. All right, so that I just wanted to make sure I at least briefly touch on everything. So let me kind of summarize this on the board a little bit again. So okay, so what do I want to say it? Okay, maybe for okay, maybe just okay, for a radiation length, actually, let me do this one just like this. So I have again, I have electrons of 10 MeV or so. They are going to undergo Bremsstrahlung and pair production. Okay, and so I can characterize this with a mean free pairs before the next interaction happens, and so the radiation length captures what's going on in these processes, right? So, and it's related to basically just the number of electrons that are there. And so if I know what material it is, I can determine the radiation lengths, and then I can model how much how far the electron travels, or how far it goes before it loses its energy. So I can use the radiation lengths and do a back of the envelope calculation. Okay. If I encounter different materials, of course my radiation length is going to change, but at least I can keep track of that in a fairly simple way still, right? For the Bethe-Bloch equation, let me again just do this. Again, this isn't for you to completely learn everything. This is meant to be an overview, right? All right, so the Bethe-Bloch equation, Hans Bethe in around 1930. So for an inch of path length, how many MeVs does a particle lose? So we need to know, if we interact just with electrons, then it's the electron density that's important. So that's in my equation here. Then I have just, of course, the electron charge and what constants of electromagnetism and the electron mass. There's this logarithmic term that's just the relativistic rise. We don't need to understand everything in detail, but for small particle velocities, we can look at this in a different way, where it's just the ionization energy of the material I'm traveling through, and basically compare the energy of the particle, the kinetic energy, to the ionization energy, and the logarithm comes from doing an integral over some cylinder. I could derive this, but I don't think I have the time to derive it. It's not hard to derive it, just from Coulomb interaction in a cloud of electrons. But it's an equation that, if I know just the average ionization potential, the chemical potential of the material, I can calculate how much energy the particle loses. And due to this logarithmic potential again, what does this really look like? I have, okay, let me go and use the board. So I have this, let me roughly plot the dE by dx, the magnitude. Of course, it's going to be negative. The particle loses energy as it's traversing material. Okay. So as a function of distance traveled, okay, it's going to be about constant, and then towards the very end it's going to rise before the particle then doesn't have enough energy. So here this is minimum ionizing particle. It travels so fast through the material that it doesn't have enough time to deposit a lot of its energy. So this is, again, it depends on the exact number, how many, MeV per unit length. That depends on the material and so on as well. But the point is, most of its energy is lost towards the last part of the path where it stops, and so most energy of charged particles. Of course, this whole thing about Coulomb interaction only works for charged particles, right? Near the end of the trajectory. So what does that mean? It means, for example, that if I use heavy ions to treat tumors, then if I can calculate the initial energy so that I know the total distance it's going to penetrate through some material, human tissue, for example, then I can adjust my accelerator to shoot an ion into the body. Here it traverses through the skin. Now it's going through healthy tissue I don't want to damage. It's doing a little bit of damage, but not a whole lot because it's minimum ionizing. And then it encounters the tumor where that should be destroyed. And it totally nukes the tumor because it deposits a lot of energy right back there, right? So if you can image the patient, you can then use this fact that most of the energy gets deposited near the end of the path to, for example, treat cancers that are localized tumors by depositing energy deep inside the body. You can further then aim from one side and then rotate the patient so that your minimum ionizing part goes through different parts of the patient, right? So that's charged particles of energies where interacting with the electrons in the atoms is the dominant mechanism, right? At higher energies, then we need to focus on all the different possibilities of interacting with the nucleus, right? Because at higher energies, I have the shorter length scales. And so I see the nucleus instead of the electrons in the atom as a whole. Does this make sense so far? The concept of a minimum ionizing particle, and then once it slows down, it spends more time near the electrons it's interacting with and it's losing more of its energy?
Yes.
All right. So again, hopefully in radiation physics, there will be enough time to revisit this in a lot more detail and to derive the Bethe-Bloch equation. But that's one possibility. Okay. I talked about radiation lengths. I talked about electromagnetic shower and the characteristic lengths associated with that. Now, the radiation lengths, and so, but what about an interaction lengths? So at higher energies, again, I have different processes available. And so now I can, do do different things, and it depends on how much energy I still have available, and am I still energetic enough to produce, a new baryon, or did I already lose enough energy so that probability shrinks, but I can still produce a pion, right? I'm still above pion production threshold. So now we need to take all these processes together. And so if I'm in a uniform material, I may still, take one number to describe all this, and have one interaction length that characterizes the hadronic processes. But in reality, things can quickly get more complicated, right? Because the environment usually isn't homogeneous, right? And so since I don't have you next time, I just want to briefly then go over the methods we can then apply to treat this. So just for those of you who've never done Monte Carlo simulations, let's try to figure out what methods we can apply. So let me talk as a side note about something totally different from radiation interacting in matter. So let's say I have a little game, and I have 100 fields beginning and finish, and I have my little toy figure, and I roll a die, and I roll a number from 1 to 6, and I advance that many fields and say, I have 100 fields. How many times do I need to roll the die on average to get to the end? Well, it's easy to calculate, right? If I have a die that rolls every number with an equal probability, then of course, on average, I roll what, 3.5, right? I'm never actually going to roll a 3.5. I'm going to roll a 3 or a 5 or 2, whatever. But the average is 3.5, right? And so to advance to 100 in steps of 3.5 on average, I just need to divide 100 by 3.5. And so after, about 30 rolls of my die, I'm going to finish the game, right? Okay, so that's very easy to calculate because it's a very simple game, right? Now, maybe you know a game called Snakes and Ladders. It's still got the 10 fields in, 100 fields, but the path to the finish from the start is arranged differently. Well, that doesn't matter, right? I still have 100 spots I need to go around, but now we make it more complicated. For example, if I end up on this spot, I can immediately advance up here with a ladder, right? Or if I end up on this spot, I have to slide back down to this spot, okay? Things like that, right? So now, how many rolls of my die is it going to take to finish this game? It's more complicated to figure out, right? We haven't changed anything about the physics. We still have a die that gives me a number between 1 and 6. We still advance by so many fields according to defined rules. But instead of having a very simple, like a homogeneous material for our particle to travel through, I now have these complexities added. So how do I find out what's going on? In principle, I could still treat this analytically, right? I could say if I end up on spot 7 or whatever it is, then go to spot 34 or whatever is up here, right? I could do all those rules, and then I could do probabilities that products of probabilities. I have probably a 1 in 6 chance of hitting that field, right? And so with 1/6 probability, I advance up to number 34, and with 5/6, I need to travel the other path. But we see it quickly becomes intractable, right? So what's the method? How do I find out how long how many rolls of the die, how many turns it's going to take to finish this game? I can just play the game 1,000 times and then take the average, right? So that's going to take me a long time, but a computer can just do it very quickly, right? I can program the layout of this board into the computer. I have a random number generator that I can let roll the die for me. And then I let the computer play the game and just write down, keep track of histogram, the number of turns it's going to take to finish, right? And so I can analyze the game with what's known as a Monte Carlo simulation, right? I just play the game. And so for particles traversing through matter, we use a similar technique. In principle, we know the physics. We understand the processes involved, right? Just like in order to model, in order to find out how many turns, well, I need to tell the computer where are my shortcuts, my ladders, and where are my pitfalls that turn me that make me go backward, right? Where are snakes and ladders, in other words, right? So I need to know everything about this, right? I need to know, am I rolling 1 die or 2 dice per turn, right? Are they actually fair, or do they roll a 6 more often than a 1, right? So I need to know everything about the physics that's going on. Similarly, if I want to simulate how much radiation penetrates through some shielding, I still need to know what are the processes that are important. What is the cross-section for a proton on, the carbon of my graphite, or, whatever, the iron in my steel, or whatever else, right? So I need to know the inputs. But once I have those, I can then at every step, right, I have the particle, and now it's got a certain cross-section to do this process, a certain cross-section to do that process. And so at every step, I can roll the dice and see, oh, is it going to interact? Is it going to scatter and change directions? Is it going to, do something else? And I determine the probabilities, or is it doing none of those things and just continues to travel in a straight line? Well, then I do that action. I move the figure down the board and see where I end up, and then I, roll the dice again. What happens in the next step? Do I encounter a boundary from one material to another? Then look up the different cross-sections for that new material and keep playing, right? So we can simulate complex situations that way, right? We can analyze the game. we can do more than that. Say I find out with a certain setup of my snakes and ladders board, it takes on average, I don't know, 30 turns, okay? Let's say I'm going to have my 4-year-old nephew visit and 30 turns, no way he is that patient yet. But he has heard about snakes and ladders and wants to play it. So I could ask, well, how do I need to modify the game so that it takes only 10 turns on average? Maybe I need to add a few more ladders, right? But where and how? So I could just play around, right? I could take an educated guess. If I add another ladder from, you know, here all the way up close to the finish, right? How does that change the game? I'm adding a bit more shielding in my simulation, or I'm changing some material, or I'm, you know, doing something else to my setup. And then I can run the Monte Carlo again and I get a new answer. Well, perhaps this ladder isn't even helpful because right here is another snake that lets me go way back down, right? Maybe after I end up here, I then often just hit that snake and maybe that's just not even helpful. Maybe, you know, I can't really tell without running the Monte Carlo, right? And so, but we can make different setups, right? I can take this ladder out again and try a different one, right? Whoops. Here we go, right? I could make my ladder connect to over here instead, right? Now I run the Monte Carlo again. That's a different shielding block in a different place. And I can see what that does, right? So that's what we mean by running Monte Carlo simulations and why they are necessary. Does that kind of make sense? So especially to those of you who haven't run a lot of Monte Carlo simulations, right? That's the idea, and that's why we have to resort to computational techniques. It's not that we can get around having to know the mechanisms for how particles interact, but it does let us analyze situations that are just too complicated to, you know, do it in a straightforward analytical way. It's still the same physics, but we need to use computational methods to analyze it, and the computational method of choice is a Monte Carlo simulation. So that then, you know, to do the snakes and ladders example, you could just write your own little program from scratch to do a shielding analysis for a spacecraft and calculate the radiation dose that the electronics board on your CubeSat is exposed to. Well, you probably don't want to start from scratch. And so the tool that's kind of the industry standard, well, there's far more than one, but GEANT4 is one particle simulation framework that's got computing routines to specify a geometry, and it knows cross sections between you know, particles of over a large energy range with different materials, and so it's the framework of choice. There are other frameworks that are used, especially for radiation assessment. There's one called MARS. There are yeah, different specialized frameworks, but in this course of study and in many applications in both particle physics as well as nuclear physics, as well as modeling. I briefly mentioned cancer therapy, to simulate those processes, to again simulate the space environment. GEANT4 is a framework that is used for that. So I was worried I wouldn't be able to cover everything I at least briefly wanted to touch on, and now I have plenty of time left. So what are your questions? What are you interested in? What made sense, what I talked about today, and what was confusing, and I should try to explain it again?
So I can imagine in the snakes and ladders analogy that instead of trying to randomly play 1,000 games, a game like Snakes and Ladders, we could play every possible game. Maybe find a couple of loops and cut those out cleverly, but we could play almost every possible game computationally, which I can almost imagine is similar to taking like a uniform distribution and trying all of those initial points. Do we do the randomness because it's less likely to get caught in some coincidental resonance sort of thing?
So, okay, right. So, there are many board games where people have been wondering, is there a winning strategy, or does suppose both players play perfect, is it an advantage if you start as white or as black, right? And many of those questions, the answer just wasn't known until we got better and better computers, and then many games have been solved, right? Meaning that the brute force approach has been used to play every possible variation, right? With chess, for example, we are far from being able to do that. Chess is too complex a game. We developed very good chess-playing computers, but they haven't played every possible game, right? There are just too many games, even given today's large amounts of computer memory and so on. It's just not possible. Similarly with Go and with several other games, but sorry, the English name for that game evades me, but one of the simple games where you that you play with on a much smaller board, it's been solved, and it turns out if both parties play perfect, nonetheless white wins because it's got the first choice, and that no matter what black does, it's kind of like tic-tac-toe is a very simple example, right? Even humans have figured out the winning strategy for tic-tac-toe, right? And we've done that by probably playing all the possible games up to, rotating the board gives you symmetry that, lets you eliminate choices. But so there you can, play every possible game, and you find that there's no winning move. If both parties play perfect, it's going to come out a tie. Nobody wins, right? There's another game where always white wins, right? And but for most situations, you can't exhaustively do that. For snakes and ladders, as you've mentioned, there's a possibility that I climb up and then slide down through one snake and go to the head of that same snake again and slide down, right? So I may have loops, And so in principle, not everything terminates. I could play the game forever, right? Extremely unlikely, but possible. So, but even if I take that into account, if I make the board large enough, the complexity is high enough so that I can't, in a reasonable time, play every game. What's the situation for modeling, even a simple, having a particle interact, a high energy particle interact, even in a uniform material? Well, at each step, I have an enormous number of possibilities, because it's not just I can produce a pion, but if I produce a pion, how much kinetic energy do I impart on it? It's a continuous variable, right? In principle, with even one continuous variable, I immediately have infinitely many possibilities, right? And in practice, I end up with, infinite to a high power very quickly. And so certainly not in every geometry you may want to examine or test, or any detector setup. But even not for one detector setup can you play all the possibilities through that a particle of radiation will have. And then, of course, what's coming in also is a statistical distribution, right? You just don't know exactly what particle of radiation is going to interact, right? You just know a distribution, a spectrum of particles. Yes, lower energies are more likely, protons are more likely than alpha particles, and alpha particles are more likely than carbon nuclei. But you don't know what's going to come next. So you even need to roll the dice to just sample your beam or your radiation particle coming in. So we really do need to resort to Monte Carlo techniques. So I had asked you to get accounts on Bioshock, and some of you did, and I hope you played around a little bit, and I hope you are going to pursue this in your spare time, and maybe just look at I know, spare time, you are laughing. I don't have any of that either, but I brought up the snakes and ladder example, not just to explain what the Monte Carlo technique is, but also, if you are totally stuck and you, don't know how to get started, you can code up just a simple model, right? If you are starting to learn how to program, just set your own problem, come up with a, don't try to solve the problem your professor tells you, but try to solve a simpler problem just to learn the technique, right? You can learn this independently and set yourself realistic goals you can model. And so, anyway, hopefully you are going to be able to do something with that. So. All right, any other questions, any other comments, anything else that was interesting where I should maybe elaborate? Well, all right, I think we have 10 minutes left officially, but again, what I tried to do today was to just give you a quick overview of the different mechanisms by which particles can interact in matter. And for that, it matters what the type of particle is. is it a charged particle or is it a neutral particle, right? A neutron will go right through until it bounces into a proton, another nucleon of its same mass. So neutron will eventually bounce into hydrogen, a nucleus of hydrogen, and then a proton will move and deposit energy, right? And up to that point, the neutron is just going to be invisible. And the neutron is going to have a much higher cross-section and something that contains water, free protons, or at least very light nuclei, and will, if a neutron bounces off a heavy nucleus, it's like tossing a ping pong ball at bowling balls, right? It's going to just bounce off, but not deposit energy into the bowling ball, right? So neutrons, just until a charged particle starts to move, they don't do a whole lot. So again, it's a random process. Do I hit a proton or not, right? Electrons behave differently from protons or other heavier particles because of at these low energies when they interact with the electrons. But then also I talked about these different length scales. If I get to higher and higher energies, different processes become important, right? Then as my particle loses energy, again, how I see the world around me depends on what wavelengths I interact with, right? What wavelengths I use to see the world around me. So then it's, the particle physics, high energy physics processes that, at the highest energies, I have quarks colliding with one another. Even if it's a proton that's coming, it's just one of the quarks of the proton that's interacting with a quark in the other proton, a parton level interaction, and the proton just explodes and the other parts are spectator quarks. Then at lower energies, all these other different processes become important, right? So yeah, go ahead.
Does that mean that at the pion mass scale, if you had a neutron, it would suddenly start to have a lot more interactions because nuclear interactions have now turned on?
So the neutron, so what's the probability for a neutron to interact, and what are the processes in which it can interact? So it turns out kind of like I said, the minimum ionizing charged particle is minimum ionizing because it goes so fast and it passes by before it can really interact. High energy neutron has higher energy, and if it blasts apart the nucleus, of course it imparts more energy, but it really doesn't, it doesn't spend enough time to really interact, and so the probability to interact, it just needs to lose energy. It needs to be, in nuclear reactors, you want to moderate the high energy neutrons down to become thermal neutrons, right? Thermal meaning low energy, because they are still moving fast, but with lower energy compared to like you and me running, but they have much lower energy than, say, the neutrons that come out of a uranium spallation. And so if you want to maintain a chain reaction, the high energy neutrons are not very efficient at being captured. And so they are probably going to leave the nuclear reactor core before they interact. But if you can have, say, beryllium mirrors and reflect them back, and have water where they elastically bounce around and lose some of their energy by pushing a proton that then loses energy, and so it bounces around a couple of times like a billiard balls on a table. And then eventually it's a low energy neutron, a thermal neutron. And then once it's slow, then the capture cross-section increases. And then it's going to blast another nucleus apart or get absorbed in a nucleus and make it be, change it from being stable to unstable. And then that nucleus breaks apart or something like that, right? But so actually lower energy neutrons have the higher interaction cross-section. Up to a point, a moment ago, when you started to ask the question, I had just explained how for basically in a particle collider, we can collide at the Large Hadron Collider two protons together, but what really collides at these very high tera-electron volt energies is not the protons, but just two of the quarks, or a quark and a gluon. And the remainder of these two particles are just spectators to that parton-parton interaction. Well, we don't have accelerators for neutrons because we use the fact that protons are electrically charged to steer and accelerate the beams. But if you had such a high energy neutron, or if you had a target rich in neutrons and shoot a proton beam into it, then at those high center of mass energies, the neutron looks just like the proton. The electric charge doesn't matter too much, and it's going to be parton level interactions. So again, the energy scale matters for what wavelengths corresponds to that energy and what interaction is, what model of the particle you need to use, both for the particle of your radiation as well as for the matter you travel through. All right, well, thanks for those questions. I hope everybody else got something out of this lecture and isn't totally confused. Again, this really is just meant to be a first overview and an outlook on what you are going to cover in the semester-long course on radiation physics. So I hope it was somewhat beneficial. And unless you have any more questions, let's leave it at this. And again, next time you will talk with Dr. Arik Kirschenbaum about exobiology. All right. Have a good evening.
Thank you very much. I enjoyed it.
All right. Thank you.
Bye.
Bye.
Thank you.
Bye.